Today's calculus lesson is about estimating finite sums, and then the definite integral and area. So let's read this first problem. The velocity of a toy car is shown in the graph. The equation for velocity is given by v of t equals 2t times 0.8 to the t. Find approximately the distance the car travels from t equals 2 to t equals 10 by counting squares. So let's talk about this. Distance traveled is always going to equal the rate times the time. So how fast are you going and how long are you going at that speed? So if we look at this axis, this is time and this is velocity. So at any given point, at time 2, this is the speed this car is going. At time 4, this is the speed, and so on. So what we're going to do is multiply the rate times the time, which geometrically is the area of one of these squares. So we're interested from 2 to 10. So we're going to count up all of these squares. 1, 2, 3, 4, 5, 6, 7, 8, and so on. So I counted 43 whole squares, or mostly whole. Some of them are a little cut off. And then I have these partial squares. So just estimate to the nearest tenth about how much you think each box is. So like this one, it's a little bit more than half, so I'd say it's like 0.6. This is less, and so on. So maybe about 0.4, maybe 0.7. It's about half, 0.5, a little teeny one, so we'll call that 0.1. Again, this is just a rough estimate. There's no, and let's call it 1.6. So I've got the 43 whole squares, and then a 0.6, a 0.4, a 0.7, 0.5. And if you count them different, like I said, that's okay. Okay, so how many squares is that? That's approximately 46.6 squares. Now let's look at the units here. If I have one square on this dimension, looking at the graph, each of those is going to be 1 second. On the y-axis, each square is 1/2 feet per second. So the area of the square is actually going to be 1/2. If we multiply feet per second times second, that's going to be 1/2 of a foot for each square. So I'm going to take my 46.6, multiply that by 1/2 to get about 23.3 feet. Same graph, but now we're going to find approximately the distance the car travels from t equals 2 to t equals 10 using a left Riemann sum using 4 intervals of even width. Okay, and then we'll answer that follow-up question. So a Riemann sum. So again, we're going from 2 to 10, and we're going to break this up into 4 equal pieces. So that's going to be from 2 to 4, 4 to 6, 6 to 8, and 8 to 10. So we're going to go ahead and draw vertical lines at all of those locations. Okay, a Riemann sum is a way to approximate the area under the curve using rectangles. A left Riemann sum, the connections for the rectangles are going to be on the left side. So we're going to start on so this first one is going to go from here to there. This one like that. Next one like that. Next one like that. So the rectangle is going to be evaluated at the leftmost point. Okay, then we're just going to find the area. So we're going to add the area of each of the rectangles. So my distance is going to be, the width of the rectangle is 2. The height of the rectangle is the velocity evaluated at 2. The second one's width is 2. The height is the velocity evaluated at 4. The next one, the velocity, width is still 2, the velocity evaluated at 6. And then the width is 2 and the velocity evaluated at 8. So there's the area of each of my rectangles. We're then going to use the calculator to help us out with these velocities. So in the calculator, I've typed in my equation given to us at the top of the paper here. So we've got 2, instead of t, I'm using x, 2x times 0.8 to the x. Now you can use the evaluate feature. Since I'm going to evaluate it at 2, 4, 6, and 8, I'm actually going to use the table. So if we go to second table set, start at 0, make sure your delta is 1 because I just want whole numbers. And then I can use these numbers from the table. We would want as accurate as we can, but for right now, let's just use 3 decimal points. So we need the at 2, at 4, at 6, and at 8. And I'm going to fill that in the notes now. So these are the values pulled from the chart, and you could also use the y1 evaluated. That works too. So if we type all this in, we get approximately 23.334 feet, which is pretty close to our last guess. Okay, we're going to continue to estimate this in different ways. This next one, we want a right Riemann sum. So on the graph, we're still going from 2 to 4, or 2 to 10, in those same subintervals. 8 and 10. This time the connections are going to be on the right-hand side. So from 2 to 4, we're going to evaluate this one at 4. This one we're going to evaluate at 6, at 8, and at 10. So the area of the rectangles, 2 times the velocity evaluated at 4, 2 times the velocity evaluated at 6, and 2 velocity at 8, and 2 times the velocity at 10. Again, using the calculator. Fill in those values. This one gets me an approximation of about 22.509 feet. For the next one, we're doing a midpoint Riemann sum. So we're still going to draw our lines. But rather than evaluating them at the right or the left, we're going to evaluate at the middle. So if we're going from 2 to 4, the middle is going to be at 3. So draw a dot. That's where we'll evaluate this one. Between 4 and 6, we're going to evaluate at 5. Between 6 and 8, we're going to evaluate at 7. And between 8 and 10, we're going to evaluate at 9. So the width is still 2, and then we're evaluating at those midpoints rather than the endpoints. You can use the calculator to get those values. When evaluated, this one's approximately 23.212 feet. We're going to do this one more way with something called the Trapezoid Rule. So on the graph, we're still going from 2 to 10, and we still have 4 even intervals. But rather than making rectangles, we're going to make trapezoids by connecting the endpoints. So there's our trapezoid from 2 to 4, from 4 to 6, from 6 to 8, and from 8 to 10. Okay, the area formula for a trapezoid from geometry is 1/2 times the height times the sum of the bases. This one, these are trapezoids. Trapezoids are defined by two parallel lines and two not parallel lines. So the two parallel lines are always going to be these vertical lines. So the bases are going to be those heights. The height of each of these rectangles is going to be the distance between those bases. So our distance, we're going to have 1/2, so we're doing 4 of these formulas. The height is going to be 2. The sum of the two bases, this is going to be v of 2 plus v of 4. And we're going to repeat this for all of them. I'm just going to work vertically just so you can see them all. So we're going to have 1/2 times 2. The next one from 4 to 6 is going to be v of 4 plus v of 6. Next one, 1/2 times 2. We're in this rectangle now, or this trapezoid. So v evaluated at 6 plus v evaluated at 8. And lastly, from 8 to 10. Okay, then you plug in the corresponding numbers and add all of these up. This one gives us approximately 22.921 feet. Okay, now there is a way to do this in your calculator. I'm going to share some notation and then we're going to define it and talk more in depth about it here in a second. This is involving the integral from 2 to 10. This is what's called a definite integral. Okay, so we can do this in the calculator. This finds the area of v of t from 2 to 4. So in the calculator, remember that our function is stored in y1. So I'm going to go just to my home screen here. If you go to alpha f2, in this menu, underneath the derivative which we've used, is fn int. So we want fn int from 2 to 10 of our y1, and we put an x there. Gives us 23.242 feet. So our approximations were all pretty accurate, or pretty close anyway. Okay, so now I'm going to write two different definitions of the definite integral. And before I do that, I want to go back to the first page. So in 1b, there was a question that said, how could we make this estimate more accurate? What we're trying to do is trying to find the actual area under the curve. Well, if I look at these rectangles, we've got some space we left out here. We've got some space that was extra that wasn't under the curve. So there's different ways we could make this more accurate. The way we're going to look at it is if I made, if I did this with 8 subintervals, then the graph is going to match a lot better. Those rectangles are going to be better. If I did 100 rectangles, if I made teeny tiny little rectangles here, okay, then my graph is going to be my estimate is going to be a whole lot better. Okay, I'm going to write two definitions for the definite integral, and then we're going to talk about them. The first definition, the definite integral from x equals a to x equals b, gives a way to find the product b minus a times f of x, even if f of x isn't constant. Graphically, so let's say we have some f of x. Here's a, here's b, which means this distance here is b minus a. So we want to find area, we multiply base times height, but our heights here are varying, they're f of x. So this times this gives me my area. So another way to think about this, like I already mentioned, is the area under the curve. Okay, so I just want you to watch right now. You don't need to copy this down. So let's say I have this curve here, and I want the integral from a to b. Okay, so I set up a Riemann sum. So I'm going to come in here and break this up into rectangles and add up those rectangles. Okay, so I'm going to partition them. Okay, this distance here is going to be some constant. Okay, so the widths of each of these rectangles we're going to call delta x, and for some reason we say delta xi. It's we don't know what it is. It's just the distance between our two different x's. Okay, we're going to pick a number in the interval, and we're going to call this xi star. Again, some of this notation's a little funky. Okay, so we're going to pick some point in each of these intervals called x star I, and then evaluate. So the height is going to be the function evaluated at this mystery xi star. And then we're going to add all of those up. So my sum, remember function notation, we're going to go from I starting at 1, so we've got x1, x2, x3, and so on, to some n of the product of these two things. So f xi star times delta xi. That's going to give me my area. Well, what we're looking for is the width of these rectangles to get really, really small. So the integral from a to b is the limit as the maximum delta goes to 0. Okay, we want the widths of those rectangles to be as infinitely small as possible of this sum. And that's, you can kind of see the structure here. So the function, the delta x and dx for this. Another way you can see this would be, instead of that thing, n going to infinity. So if we want the number of rectangles to basically be infinite, that's another way to write this same thing. Okay, so our other definition of the integral from a to b of f of x is the limit as the maximum delta xi goes to 0 of the infinite sum from 1 to, sorry, this should be n, of f of xi star delta xi. So if you need to pause to write that down. So College Board expects you to be able to go between those two different forms, going from the limit form to the integral and the integral to the limit. This would typically be a multiple choice question. So it's not necessarily that you have to have this whole thing memorized, but just recognize the different parts of it. So this is the Riemann sum definition of the integral. So we're going to write this as an integral. It gives us 1 to 2. Now we need to identify the function. So in the general case, it's just f of xi star. In this one here, instead of that, we have xk, and it can be a different letter, xk star cubed. So this is just the function x cubed, and then instead of delta x, we have dx. Okay, going the other direction, we're going to have the limit as the max, delta x I or k, doesn't matter, goes to 0 of the sum from k equals 1 to n. Now here we're doing this, so it's just going to be 2 cosine, but instead of x cubed, we're going to have xk star cubed delta xi. Okay, So we're going to write this, the limit as n goes to infinity of k equals 1 to n of 2 plus 4 over n k cubed 4 over n. So let's break down what this is. This is a Riemann sum. You have a width and a height. The width is going to be 4 over n. So we're taking a spread of 4 and dividing it over n. So my delta, my change in x, is going to be b minus a over n. So I'm going from a to b. I'm going to split that up into n pieces. So that means here my spread between my bottom limit and my top limit is going to be 4. There's different approaches to this. What I'm going to look at first is where does this start and where does this end? It's going to be a spread of 4. And if I look at plugging in these values, if I plug in k is 1, then we're going to have a starting value of 2 plus 4 over n times 1. Well, n's going to infinity, so this is going to start at 2, because that's going to go to 0. The ending, we're ending at n, so that's going to be 2 plus 4 over n times n. The n's are going to cancel, so we're going to have 2 plus 4, which is 6. So we're starting at 2, we're ending at 6. Then we're looking at what we're plugging in. So our widths, my next one here is going to be 2 plus 4 over n, because we're adding, this is my delta. So we're taking this and plugging it into this function. And this is tough to get, plus 2 of 4 n's. And then we're evaluating it in some function. The function is going to be this cubed. So this is going to be the integral from 2 to 6 of x cubed dx. The other way to see this would be your starting value, and then you're looking at that as your function. Okay, here's another one. Again, just understanding that this is a Riemann sum, that we have a width and the different heights. So we have some function. To get the bounds, you want to look at the limit as this goes to infinity and the limit as this goes to infinity. So as this goes to infinity, that's going to be 0. As this goes to infinity, the n over n is going to be 1. So my limits of integration, is what we call these, are going to be 0 to 1. So e is not our thing. So the 1 on top, again, is going to be the distance between the top and the bottom, or the 2x values. And then we're taking that, so we're starting at 0, we're ending at 1. My deltas are 1 over n. So this is going to be 1 over n, this is 2 over n, as we add those, because the widths are 1 over n. Then we're taking that and plugging it into something. So the something in this case is something squared. So this function is just x squared, which is going to be b. The 1 over n, you might be tempted to say it's like 1 over x squared, but it's the value that we're plugging in is that 1 over n. Okay, this is another similar one. So first, our spread is going to be 1. In this one, we're specifically breaking it up into 10 rectangles, but we have a spread of 1. So C and D are out. This one is going to be 0. This one limit would be 1. So we're from 0 to 1. And again, the function that we're plugging it in is squared. This is a Riemann sum, so this is our width. These are our various heights. So this 1/10 is just not a part of that. Okay. Now we're going to do a Riemann sum from a table. So the table shows a continuous function using the subintervals from 1 to 3, 3 to 6, 6 to 8, 8 to 12. With these different values. We're going to approximate the integral from 1 to 12. using the trapezoid rule, a left-hand Riemann sum, and a right-hand Riemann sum. So the trapezoid rule is going to be 1/2. The height of each of the rectangles is going to be the change in x values, the width. So this one's change is going to be 2, this one's 3, this one's 2, and this one's going to be 4. So my width is 4. For the trapezoid, we use both of the endpoints. So 4 plus 5 plus 1/2. The second one's width is 3. 5 plus 1. Our third trapezoid, 1/2. Its height is 2. We have 1 plus 3. 1/2 times 4 for this one. 3 plus 4. When you plug all that in, you'll get 36. The left-hand Riemann sum, we're doing rectangles now. So it's going to be the width times the height, and the height is going to be evaluated at the left side of the rectangle. So my first width is 2. The height for the first one, we're going to evaluate at the low end, so 4. The next one's width is 3. Its height is 5. The next one's width is 2. Its height is going to be 1. The last one's width is 4, evaluated at the left side at 3. All of that together is 37. The right-hand Riemann sum, we're going to have the same widths, 2, 3, 2, 4, but now we're going to evaluate at the high end of the range, at the left-hand side, or on the right-hand side. So we're going to have 2 times 5 plus 3 times 1 plus 2 times 3 plus 4 times 4 is 35. So we've defined definite integral in a couple different ways, but the basic idea is the integral is the area under the curve. So what we're going to do here is make a graph and then use geometry, good old geometry, to find the integral value using area. Okay, so our first one, we have the integral from -2 to 1 of 5. So if I were to graph the function y equals 5, that's just going to be a horizontal line. So we want the area from -2 to +1. So this is our area that we are going to find. This is going to be the definite integral. So we'll multiply the width times the height. So this is 3, this is 5. So this area is going to be 3 times 5. So the integral is going to be 15. Here we've got from 2 to 4 of 2x plus 1. So we'll go ahead and graph that. Okay, so 2x plus 1, we're going to cross at 1 and then go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. I switched my colors. So we want the integral from 2 to 4. Okay, so this one's going to be a trapezoid. So the area of the trapezoid is going to be 1/2. The height of the trapezoid is going to be 2, and then the two bases are going to be the two different function values. So at 2, we plug in 2, we're going to get 5. If we plug in 4, 2 times 4 is 8 plus 1 is 9. So this one has an area of 14. Okay, this one is the area formula for a semicircle with a radius of 5. So I'm going to go 5, 5, -5. So my function is just a semicircle, and we want the area from -5 to 5. So this one's area is pi r squared, 1/2 pi r squared. So this is going to be 25 pi over 2. Okay. Our next one, x from -1 to 4. So y equals x, just a straight line here, y equals x. This one, we're looking from -1 to +4. So it's this, and it's this. So we have two triangles here, but one of these triangles is below the x-axis. And if you're doing an integral, if it's under the x-axis, this area is going to be negative, this area is going to be positive. So this is going to be this triangle, which is going to be -1/2 base times height, which is 1 and 1, but it's got to be negative if it's below the x-axis. And then here we'll have plus 1/2 4 times 4. So we'll have 16 over 2, which is 8, minus 1/2. So this integral is 7.5. So even though we're using area, the area I shaded isn't 7.5, but the integral is 7.5. Okay. The absolute value of 2x plus 1. There's several ways that you can think about graphing this, but I'm going to start by just graphing the line 2x plus 1. Go here, but then it's going to bounce up because it's the absolute value of that line. So my next dot is going to be here and here. So I want the integral from -3, so there's -1, -2, from -3 to +2. So that's going to be two different triangles. The width of the rectangles is going to be 2.5, so 1/2. This one is 2.5. The height, if I plug in -3, that makes this -6 plus 1 is -5. Absolute value of that's going to be 5. This one's also 2.5 and 5, so I'm just going to plop a 2 in front of that to say I have two triangles, or you can add them together. This is going to be 12.5. Okay. This one's integral. We're going the integral from 0 to d of f of x. So all we're going to do is we have above, below, above. So this is going to be whatever the area 1 is minus whatever the area of 2 is plus what the area of 3 is. This is the same thing but with values. So we want the integral from a to c. So a to c is going to be 1.8 minus 2.3, which is going to be -0.5. From a to d is going to be 1.8 minus 2.3 plus 1.4. which is 0.9. Okay, next one, I am again going to go ahead and graph this piecewise function. So when x is greater than 0, we have the line 2x. So 0, 0, up 1 over, 2 over. And then when it's less than it, we have -3. So we have a closed dot here, an open dot here. So there's our graph. So the integral from 2 to 3, so here's 2, here's 3, that's going to be a trapezoid. So that's going to be 1/2 the width of the trapezoid. The distance between 2 and 3 is 1. And then if I plug in 2, we get 4. If we plug in 3, we get 6. So this is half of 10, which is 5. From -5 to -2, that's going to be a rectangle. It's going to be negative because the area there is negative. The width of the rectangle is going to be 3 between 5 and 2, and the height is also 3. So this integral is -9. From -3 to +2, we have to break that into two parts, the rectangle and the triangle. So from -2 to 0, that's going to be a -2 times 3 for that rectangle. Sorry, -3, because the width is, we're going from 3 on, sorry. Plus the area of the triangle, which is going to be 1/2. The base of the triangle is going to be 2. The height of the triangle is going to be up at 4. And it may help to graph this. I just didn't want a bunch of graphs on the same thing. So this ends up being a -5. And I realized you haven't been able to see any of that. So we have -3 to 3 for the rectangle. And then 1/2, 2 times 4 for the triangle gives us a total of -5. Okay, this one's kind of funny. This one, if we factor, is going to be 3 minus x, 3 plus x over x minus 3. Well, these are basically the same but opposite. So this is really the same as a -1. So this is going to be the integral from -5 to 6 of -x minus 3. So that's just a line. I'm going to go ahead and draw that line. So here's the line, -x minus 3. Have a negative slope, negative y-intercept, and we want the integral from -5, which is going to be right here, to 6, which is all the way here. So again, we have two triangles. One's above the x-axis, one's below. For the one above, we're going to have a positive 1/2. That's going to be 2 times 2. Below the x-axis, we're going to subtract that triangle. So 1/2, this is -3 to +6, so that's going to be 9. And the height's going to be 9. So this ends up being, if you plug it all in, -77 halves. Okay, our last set of problems here says if the integral from 0 to pi of sine of x is 2, we're going to use that information to find some various things. So let me graph this. So sine goes from 1 to -1. Okay, so there's sine. So this is telling me that the area from 0 to pi is 2. Okay, so from that, we can answer some other questions. So if the integral from 0 to pi is 2, we want from pi to 2 pi. Well, this is going to be the same area, but negative. So this is going to be negative 2. For b, the integral from 0 to 2 pi, so from here to here, is going to be 2 minus 2, which is going to be 0. From 0 to pi over 2, well, there's pi over 2. So it's just going to be half of that, which is going to be 1. For 2 plus sine, we're going from 0 to pi. So what's going to happen here is the bump is going to go from here to here. So this area is going to be 2, but we still need this area as well. So we're going to have the 2 plus the area of this rectangle, which is going to be 2 times pi. Okay. The integral from 0 to 2 pi of 2 times sine of x. Graphically, it's going to change the amplitude. There is just a rule for integrals that if you're multiplying by a constant, you can pull that constant out. So this is going to be 2 times 2, which is 4. This one just shifts everything to the right 2. So we're going, here's 2, here's pi plus 2, and there's sine of x minus 2. So this is just 2. From negative pi to pi, okay, so from negative pi to pi is going to look like this. So that area is going to be 0. Okay, this one, x over 2. So you have to think back to pre-calc. The period of this is going to be 2 pi divided by 1/2. Which is 4 pi. So rather than it doing one of these cycles from 0 to pi, it's going to go from 0 to 2 pi. So it just stretches it. So this is actually still going to be 2. And then the last one, 0 to pi of cosine. Cosine starts at 0, goes like that. So whatever this area is, which is 1 and 1, they are going to cancel each other out and be 0. So that is how we can find definite integrals geometrically. Our next lesson will actually figure out how to do that analytically.